Okay, so good morning, everyone. And I have released the midterm exam sample. Let's not say midterm one exam sample because I am not going to release midterm two exam sample because you get the idea, right? And by the end of midterm one actual exam, you will have the idea of an idea of the exam anyway. So also, I made an announcement and I mentioned there that one of the question in that sample is about CPU scheduling. Just ignore it. It doesn't mean that I'm going to cover the CPU scheduling chapter in the midterm exam, first midterm exam. So as I said in the last lecture, the syllabus that will be covered in first midterm exam will be up to chapter 4, okay? Including chapter 4. Now, before we start our 2 days lecture, any questions from the previous lecture? Nothing. How is project going? Everyone is able to make progress. If not, go to the TAs. And if TAs are not like, they cannot help you or they cannot answer, then you can come to me, okay? So, okay. So today we are going to talk about threads. Previously, we have been talking about processes, right? And how processes, they can communicate with each other. What are different mechanisms? What are the trade-offs there? So until that, we were considering a single-threaded process. Now, let's talk about multi-threaded processes. But for that, we first need to build the case for the multi-threaded processing, right? So here is a motivating example. So suppose that you are using a word processor, like, for example, Microsoft Word. So, and then it needs to do multiple tasks, and you have observed it. For example, when you are writing the text, at the same time, your Microsoft Word is also doing the spell checking. So it is doing, it is monitoring your keystrokes at the same time as it is doing the spell checking, and also it is then updating your screen or your display at the same time. So at least, let's say 3 tasks are done at the same time simultaneously. How we can do this? If we have single-threaded processes, so how we can achieve this? So let's say this is the skeleton of our application. So you have a main function, and within which you have some other functions like task 1, task 2, task 3, which are doing 3 different tasks, like, for example, spell checking or monitoring the keystroke and updating the display. Now, if I want to do that, if I ask you this question, that how we can do these 3 tasks simultaneously, what will be your answer? Assuming you have no knowledge about multi-threading.
Just a while and on each task.
In while loop, but then even in the while loop, you will first execute this task, then this task, then this task, not at the same time. So one after the other in the sequence, right? So how can you do it like at the same time?
They're on one function.
But even in the one function, if you put the body of all these 3 functions in a single function, the body of that function will also be executed sequentially. Okay, here is a hint. You can learn something from project 1. Yeah.
Well, we can just update and do grammar check whenever the keystroke happens. So we only listen for the keystroke.
Yes, but still only one instruction can be executed at a one core. Let's say we have multiple cores, but even what you're saying, if we follow that, only one instruction will be executed at a time on one core.
Same just to open like process for each one.
Yeah. So that's like, I mean, if you have no knowledge about multi-threading, you have only single-threaded processes. So what you can do is like for each one of them, launch a separate process. And then if you have multiple cores, then those processes can run at the same time on 3 different cores. Now you can take care of your 3 tasks simultaneously. So if we can do this using processes, why we even need multi-threaded processes? So all those 3 processes are single-threaded, each one of them. So why we even need multi-threading processes, or idea of multi-threading? So This is what you have, one of your friend has said. You can launch 3 separate processes for handling the 3 tasks. But there is problem. Okay. Anyone who can tell me or any guess about what problem we can face if we launch multiple processes? If you remember from the previous lecture, for each process, you have to allocate the memory, because each process has its own memory layout. It has its own text segment, its own data segment, its own stack, and its own heap. And not only that, even kernel needs to maintain the information or the metadata about each process in the process control block. So earlier you were having like only one process control block and smaller footprint. Now you have 3 processes. For all 3, you are first occupying the memory, one thing, and second, you are also maintaining 3 PCBs. So you have more memory consumption, because now you can see you have like for process 1P and process 2 and 3, you have 3 memory layouts. Okay, I will keep talking. The screen will come back. So, and as I said, on top of that, you need 3 process control blocks. So irritating. Yeah, so now you need to control, now you have to have 3 separate process control blocks for each one of them, which mean each one of them also take the space, and also then kernel need to do the management of them, which will take extra time, right? However, what we can observe here is like, since these processes were like more or less they are doing the same task. Not same task. They are not doing the same task, but there are some observations. One, all of these 3 operations or all of these processes, they operate on the same global and dynamically allocated data. Because when you are running the web, like your let's say Microsoft Word, so same data is displayed on the screen, which is coming from your keystrokes, and the spell checking is also applied on the same data, right? So the basic data on which the 3 processes are acting on or operating on is the same, right? One thing. Second, in the initial version of your process where you had only a single process, so you had a single code, but the 3 functions were like located at separate locations, right? Each one of them is located at a separate location within that code. So the overall text segment is same, but the particular operation which you need to perform is located at different location within that text segment, right? One thing. Second, if okay, so the basic data on which all 3 operations need to be performed is the same, one thing. Second, even if that original process, which was a single process, even during the execution of that process, if you are allocating some data dynamically, it was allocated on the same heap and was visible by all 3 operations, even like when you had only 3 functions within the body of a single process, right? So the same global and dynamically allocated data, which is operated on by the 3 different operations, also As I said, all three operations, they are coded in the same text segment, but maybe at different locations, but the text segment is same. And third, however, all of those three functions, they may maintain their local variables. But if maybe you have you taken any course which talks about function frames? When a function is invoked, what happened? So what happens is that when you invoke a function frame is created. And when the function frame actually means that you have a separate stack for each function where you store the local variables of that function, or the parameters passed to that function, or the values that need to be returned. Okay. So which means that every function has its own local variable. And maybe from the programming concept, you know it, that the local variable of one function are not visible to the other functions outside. They are not visible outside that function. The scope is local, right? That's why we name them as local variables. So each of those functions or each of those operations, they have their own local variable. So what we have observation is that heap and data segment, they are common for all three operations. Text segment is also common, with the small difference that the three operations are located at different points within the text segment. However, each one of them maintain their own local variables or local stacks. So what we can do, so what do we learn here from here? There is a common principle that if there is something which is common, then factor it out, right? So like then share it. If it is common, share it among all the participants. But if it is not common, if it is private to someone, then have a separate copy for that private entity. Okay. So what we can do here is that we can maintain the separate copies of the sorry, here is a mistake. We need to maintain the same copy of the same text data or heap segment to avoid the memory wastage. And then instead of maintaining the text data or heap segment separately for each process, what we can do is that we can have a single copy of these three segments. But then as a result, what will happen that we will reduce the overall memory. If you just imagine that in this figure on the right, you have one heap segment, you have one data segment, and you have only one text segment for all three processes. Okay, but you have three separate stack segments, one for each one of them. Okay, so what will happen as a result? Overall, you will reduce the memory footprint for your application. Also, you will also reduce the size of the metadata, which basically means the process control block. So previously we were having three PCBs for three processes, but now what you can do is that you can manage all the information within a single process control block. However, the problem is, so here is what we are saying, that traditionally you have three processes, P1, P2, P3. What we are now suggesting is that, okay, share this code, data, and files across three processes, but each process still will have its own copy of register, program counter, and stack. But the problem is that text segment, data segment, and heap of one process is not visible to the other processes. This is the abstraction of a process, the idea of the process, that any of these memory segments of process one, they are not visible to the process. So what we are trying to achieve is not possible, right? So if we stick to the traditional definition of a process, we cannot do that, okay? So that's why we introduced the idea of the threads. So the idea of thread is that what we do now is that we have a common code, data, and file segment. So the shared resources are same. And then for each thread, we maintain separately the register, the record of the registers which are used by that thread, the stack pointer, and the program counter. Okay, but the state segments are the same. Now, what happens if you consider that example, and each one of these threads, they are executing one process, one operation, like spell checking, displaying updating the display, and monitoring the keystroke. They can access the code and data and files, whatever are open, but then each one of them have their own register, stack, and PC. So as a result, we are reducing the memory footprint, we are also reducing the number of PCBs which are needed to run this application. So lower memory footprint and lesser metadata. So thread is actually a basic unit of CPU utilization, which means that if you want to allocate the CPU for execution, the smallest unit for that is the smallest entity that can execute on a CPU or that can occupy a CPU is a thread. Okay. So basically, and the idea of the thread is that it is just a sequence of execution. And that sequence of execution is actually controlled by PC resistance flag. How? Because you know how program counter works, right? It points to the next instruction to be executed. So now if there are 3 streams of execution, which means 3 threads, then you will need 3 separate PCs to track each one of them. Any questions? So now what advantage we get out of it? Some advantages I have already mentioned, that now you have lesser memory footprint, you have lesser metadata to maintain at the kernel level. But besides that, we also get the advantage of responsiveness. For example, in context of our Microsoft Word application, reading keystrokes is not slowed down due to the spell checking. Why? Because there is a separate thread which is monitoring the keystrokes and a separate thread which is responsible for updating the display and performing the spell checking. Also, as a result of threads, there is easier resource sharing among threads as compared to resource sharing among processes. If you have started working on project 1, or even if you have read the description of the project 1, maybe now you are aware that if you want to share resources or you want to communicate among 2 processes, you need to first create maybe the shared memory region, or if you want to use the message passing, you have to have the support for message passing mechanism at the kernel level. And that is expensive because you are doing the system calls all the time, right? So, but if you are using the threads, you don't need to explicitly arrange the shared memory or files. Why? Because by the definition, threads belonging to the same process, they share the code, data, and files. So you don't need to do any extra work to share the data among threads or to share the files among threads, because the code, data, and files, they are visible to all threads belonging to the same process. But code, data, or files of another process are not visible to the threads of a different process. Also, I have mentioned this already, that using multiple threads instead of using multiple processes results in lower memory space. And another advantage is that you have faster context switching among threads. Why faster context switching? Can anybody explain or try to elaborate that point? Context switching, why context switching in threads is relatively less costly as compared to context switching of processes. You'll focus on the figure, it is clear from there.
Since it's all happening inside the same process, you don't have to switch.
Yeah, you are in the right direction, but maybe you need to say it out in a better wording. When you do the context switching among processes, you need to store more information and reload more information. For example, in case of processes, you need to store the pointer of the code segment, the pointer of the data segments, the limit information of different memory regions. You need to store register, you need to store stash, you need to store PC, you need to store the information about the open files, right? So that when you in the future you need to run that process again, you can restore this information and run it. But in case of threads, let's say if I'm switch from thread 1 to thread 2, I need to store lesser amount of information and reload lesser amount of information, like only register, stack, and PC. And remember, in one of the previous lecture, we said that on some architecture, there is a single instruction which can store all the registers into the memory and reload all the registers from the memory into the values from the memory into the registers. So it becomes much less expensive to do the context switching among threads as compared to the context switching among processes. Okay. So also, multiple threads, they provide us the advantage of performance scalability, which basically means that if we increase the number, assuming that we have multiple cores on the platform at the hardware level. So if we increase the number of threads, we can reduce the execution time of the application. But this is not the case for the single threaded process. So if you have a single threaded process, doesn't matter if you have 2 or 200 cores, you cannot run it on multiple cores because it has only one thread of execution, so it can run only on one core. It cannot take advantage of multiple cores. So its performance doesn't increase with increasing the number of cores, right? But the performance of the execution time of the multi-threaded application or multi-threaded process, it reduces when you increase the number of cores because each thread can be run on a different core ideally, okay? So more thread, as long as they are less than the number of cores, you will have lower execution time. Any questions? Okay. So now if we go back to our first example where we had the skeleton or the pseudocode of the Microsoft Word. So what you can do is that instead of calling 3 functions, what you can do is that you can create 3 threads and you can assign these tasks to one of those threads, like assign task 1 to first thread, task 2 second thread, and assign task 3 to the third thread. Okay. So in this way, now you can solve the problem. Okay. Relationship between threads and cores. So we have talked about the abstraction or the idea of the threads, how they need to be, how they can help in increasing the performance, how they need to be managed, what information you need to maintain for each thread, right? But what is the relationship between the physical cores or the hardware cores you have and the threads? So thread itself is nothing, but it is just a sequence of code execution, right? Which is tracked by the program counter, among other things. At least you must have the program counter too, because you need to know which next instruction you need to execute, right? So let's say if we have a single core, but we have multiple threads. Can we achieve concurrency? To answer that, maybe you first need to know that, and maybe can we achieve the parallelism? So there are 2 questions. You have a single core, but the software or the application you are running is multi-threaded. So can we achieve the concurrency for when we execute that application? And also, can we achieve the parallelism? But to answer that, you first need to know what is concurrency. So concurrency is the case where we allow multiple tasks to execute our time, not simultaneously, our time. So can you try to answer this question? That if you have a single core, your application is multi-threaded, when you run it, can you achieve the concurrency or not? Yeah.
So you can achieve concurrency because you can schedule these tasks.
Yeah, we can do the time sharing. So you can allocate the budget and you can say, okay, let the first task run for 1 second, then the second task for 1 second, and so on. Okay. So here is like you have a single core and the time is increasing toward right. So what we see is that, okay, if you have 4 tasks, so you can schedule them T1, T2, T3, T4, again T1, T2. This is very simple scheduling algorithm, but it conveys the idea that you can achieve the concurrency using the single core. However, what about parallelism? But for that, we first need to know what is parallelism. It means that we allow multiple tasks to execute simultaneously at the same time, not our time, but at the same time. So can we do that? Obviously not, because we have a single core and that single core can be occupied only by one task or by one thread at a time, right? So, however, if we have 2 cores, then we can achieve the parallelism. Core 1, let's say at this time point, core 1 is occupied by task T1 and core 2 is occupied by task T2. And then in the next time slot, maybe T3 is running on core 1 and T4 is running on core 2. So still here you have core sharing, but across the cores, there is parallelism, right? Any questions? Okay. So this is an example of the case when software abstraction needs the hardware support, which basically means that even if you have at the conceptual level or at the software level or abstraction level, you can support the parallelism by introducing threads. But if your underlying hardware doesn't support multiple cores, you cannot actually achieve the parallelism. So the two things need to go hand to hand. I don't know if that is the correct word, hand to hand or hand in hand. So anyway, also the other way around it is true. Like if you have multiple cores, but you have no support for software threads for the threads at the software level, you still cannot achieve the parallel. Just like, for example, you have a single-threaded application running on a multi-core platform. Still, you will have no parallelism, right? Okay. So what are the challenges of parallel programming, which basically mean what are the challenges of developing the multi-threaded applications or multi-threaded processes, right? So first is to identify the tasks. So I mean, if you have an application where you can readily identify that, okay, it is performing, just like our example, it is performing multiple independent tasks, and you can then allocate those tasks to different threads, then you can easily achieve the parallelism. But if it is different, it is difficult to identify the tasks which can be performed independent of each other, then it is difficult to achieve the parallelism, right? So here is an example. So let's say you have an array having 12 elements, and what we want to do is just to find sum of all the elements. I know it's a very simple example, but it conveys the idea, what I mean. Okay, so what we can do is that one case is that, okay, we have one thread and it sums all the elements, right? But then it will take time. But here you can easily identify that if we break it down into 4 chunks or 5 chunks, whatever, so and assign each one of them to separate threads, then you can complete the task earlier, and you can allocate each task to different threads and achieve the parallelism. So here is the example. What we are doing is we are like slicing the data into 4 chunks, assigning each chunk to a different task, which is performed by a different thread, and then at the end summing up all the data. Actually, it is very similar to your project one, right? So however, so this is the case we can easily identify, right? But now let's say you have another application, you have the same data, but on this data now you are doing something different. You are doing some different operation. What you want to do is you need to update all the elements in a sequence, such that new value of an element is equal to its old value plus 2 left elements, which basically mean that, let's say I'm skipping the first 2 cases, but let's start from this one. So for third element, the new value should be equal to 3 plus previous 2 left elements. So 1 plus 2 plus 3, 7. And then for the new value for fourth element is 4 plus 3 plus 7. So this is the updated value of 3, right? So which basically means that you cannot calculate the next value until the previous value is already produced, right? So there is a sequential dependency. Now, maybe you can, so I mean, at a first look, it looks like it is difficult to identify, perform the task on the separate chunks of the data independently. But maybe you can come up with an algorithm if you think deeply, so that you can still do the task. You can still process, let's say, that data in 2 different chunks independently, maybe. Okay, but it is not relatively as easy as it was in the application one, right? So if you cannot do that, then you cannot achieve the parallelism. Even when you have the abstraction of the threads and when you have multiple cores, but you are unable to divide your application into multiple tasks, then you cannot achieve the parallelism. So it is challenging, one thing. Second challenge is that task balancing, which basically, again, we have the same example, let's say application one. So task balancing, here all of our tasks are balanced in the sense that all of them are performing the same amount of work. Each one of them is processing, like task 1 to task 4, each one of them are processing only 3 elements, right? So, but let's say we have a situation where we have only divided into 2 tasks. First task take care of the first 3 elements, and task 2 take care of all the remaining elements. Now what will happen that task 1 will be completed earlier, task 2 will be completed relatively later, right? But this is not a good idea to do that. So for our target should be able to do the task balancing, one thing, but then it is not always easy to do the task balancing, depending upon the situation or the use case of the application, right? Here, definitely it is a try example, so I'm just trying to demonstrate the idea, but in real life, a real example, maybe it is not easy for you to allocate same amount of work to each task. So what will happen if we don't balance the task? What is the downside of not balancing the tasks?
So we end up just wasting more time than we would have gained by just doing it.
That's true. If we allocate the same amount of work to each task, so it means that they will take around more or less the same amount of time to complete, right? But here, what will happen? Task will complete earlier. This will complete later. But as a whole, we need to wait for this thread to complete before we say that our application is complete, right? So it will take more execution time. This is basically underutilization. We are not utilizing the other cores, resulting in longer time to complete the overall computation. Okay. Data splitting. Again, we had the same example. We are trying to find sum of all the elements. So the idea of the data splitting is, so here if you look here, let's say task 1 is operating on the first 3 elements, task 2 on the second, and so on, next 3 elements and so on. So this is the ideal case. So task 1 is running on core 1, task 2 is running on core 2, and so on. So what we do is that we put the data which is operated on by task 1 in the L1 cache of the core 1, right? So basically we are putting the data closer to the core where the task itself is run, where the code is run, right? Same is true for all the cases. So here what we are doing is we are doing the ideal data splitting. So we are doing the ideal data splitting. So which means that if a task needs the data, it's find it is as close to its core as possible, right? But now compare it with the case where we are not able to do the ideal data splitting. Task 1 is running on the core 1 and it needs the element 1, 2, and 3, but somehow we are not able to place that data closer to the core 1. So what will happen that it needs this data, then it will access it or request it from the other core, and as a result, it will take more time, and it also will generate some other unnecessary traffic in your system. And as a result, your overall execution will be slowed down. You will still be able to complete the task, but in a longer amount of time. So you will have extra head of fetching the data from the places which are not closer to you. I'm using here the general words because I don't want to be very specific about how things work, but I'm just trying to give you the idea that what is data splitting and why it is needed. Okay, let me finish this and then we can take the slide. Right. Okay, data dependency. So again, we have the same example. Now it is clear from this figure that task 5 should be completed only after all 4 tasks, 1, 2, and 3, 4 are completed, right? So it must wait. Here, what we are doing actually is just like in your project 1, we are summing the partial sums, right? So we need for all the partial sums to be available before we can calculate the overall sum. If we don't do that, then what will happen? You will have a corrupted result, right? Okay. Another challenge is with the multi-core programming or parallel programming is testing and debugging of your applications. Again, let's say we have the same example, and now let's say that you run your application for the first time, and there was something wrong with the code of task 1, or some error happened, some corruption happened because of some reason in the task 1, the code executed by the thread 1. Okay, and as a result, the partial sum calculated by this thread 1 was not correct, and as a result, your overall sum were also not correct, right? So you are now trying to understand why I'm not seeing the correct overall result, and you are trying to debug. So what you do is that you run your application the second time, to understand it. And what happens, let's say that this time that error, there is some error in your code and it is dependent, let's say, on some event, and this error is triggered by that event, but now in the thread 3. Your thread 1 was doing fine. The error was not triggered here, but it was triggered here. Okay. Now what you will see, yes, still I'm seeing the wrong result, but this wrong result is not same as I saw it in the last time. So it will be very difficult for you to debug as compared to the case where you have a single threaded application. Why? Because in a single threaded application, you have say one sequence of execution. Here you have multiple sequences of execution. And this is a very simple case, a very simple example. But these multiple sequences of execution or threads, they also need to, sometime in depending upon the application, they also need to interact with each other. So they can affect the execution of each other. So let's say if there's something wrong here, depending upon how they interact or the sequence of interaction between them, maybe task 1 can affect in a wrong way the execution of task 3. Next time you run it, maybe it affects the execution of task 4, right? So it is very difficult because the sequence of the events is not deterministic. And if something is not deterministic, you cannot reproduce it. So if you cannot reproduce an error, it will be difficult to debug that error. Okay. So as a result, testing and debugging becomes more challenging in multi-threaded applications as compared to single-threaded applications. Okay, let's stop here and we can have 5-minute break and then we'll come back. Okay, one thing I wanted to discuss was about evaluation, instructor evaluation. I released it, I guess 2 days ago. But yesterday I checked, only a couple of students have provided the evaluation. So I would encourage you to go ahead and do it because this is helpful not only for me, it is helpful for you because based on this, I can improve myself for rest of the semester and also for the upcoming offerings of the same course. So that I can improve the content or I can improve the way how I teach. And one more thing which I want to discuss, according to the schedule, we are going a little bit slow. I mean, within this week, I was supposed to complete the topic of processes and concurrency, but I don't think I will be able to. Maybe it will take one more day. So the quiz 4 is, I guess, already released, or it will be released today, I guess. It will be released today, which is about the chapter 4. So, I mean, the quizzes and the topic we are covering are like little bit out of sync. So I will ask the TAs either to slow down or release one more quiz related to chapter 3, right? So that overall our total number of quizzes are the same, 12. You have still the flexibility to perform bad on 2 of them, but maybe the overall material we covered is less than what we intended to do. Okay. Okay, let's get back to the lecture. So the next thing we are going to discuss is type of parallelism. So what we have seen until now is that, okay, what is the concept of threads? How the abstraction of thread need to also be supported by the underlying hardware, and also what are the challenges of multi-core or parallel programming. But type of parallelism basically mean that either how we achieve the parallelism. Do we achieve it at the level of the code, or we achieve it at level of the data, or both of them? So the data parallelism basically means that we distribute the subset of the same data across multiple cores and same operation we perform on each. So here is like here is the graphical depiction. Let's say we have the same array, and we have one array of data, and we have operation to perform on it. This is very simple to what our project one was and what the example we have seen earlier, right? So we are doing the same operation like summing this chunk of data, first chunk of data, summing second chunk of data. The code itself is same, logic of the code is same, like addition. But the data on which you perform the addition is different. So what you are doing is that you have the same code running on different cores and doing the same thing, but on different piece of data, right? As compared to this, we have task parallelism, where what we do is that we distribute threads across cores, and here also we are distributing the threads across core, but the difference is that we perform the unique operation on different or the same data. So here the operation was same. Everyone was doing addition, but on different data. Here, your data is same, and you are doing different operation. So you have like thread 1 running on thread 0 running on core 0, thread 1 running on core 1, and so on. So which actually represent different tasks. But let's say thread 1 is summing all the data. Thread 2 is doing the multiplication of all the elements in the array. Thread 2 is the next thread is, let's say, doing the multiplying all the elements with the single constant, right? And so on, right? So basically here what you are doing is that your task or the threads, they are doing actually different logic or different operation on the data, same data. And that these two kind of operation parallelism, they are not mutually exclusive, which means that you can have the cases or you can have the applications where you apply both, where maybe some threads, they perform the same operation on a different amount of data, and there are also some other threads which actually have the same data but perform different operations within the scope of the same application. Any questions? But still, you need to have the abstraction of the threads and multiple cores to enable them to run at the same time in both cases. Okay. The question now, if we are running multiple threads, it is obvious, and you have maybe now seen it from your project 1 and in the example, you have got the idea that if you have multiple threads, you are able to reduce the execution time, which basically means you will get the speed up, right? As compared to the even like in scope of your project 1, if you have a single process, it will take more time to complete the task. If you have multiple processes, it will take less time to complete the task. So there is a speed up, right? So, but the question is that how, if you have multiple, let's say you have multiple threads, then how much speed up you can get compared to the case where you have a single threaded application, okay? So this is defined by the Amdahl's law. So it actually gives us the potential performance gain or the speed up with multiple cores. If you have multiple cores and you have multiple threads running on them, okay? So here what we are assuming that the application which we are running, it has both serial part and the parallel part. Parallel part mean that part which you can like, the parallel parts mean that you can assign it to different tasks or different threads, and they can run independently. But then there is some part of that same application which cannot be broken down into multiple tasks. You remember I said we need to identify the task. Let's say there is some functionality of the application which can be broken down into multiple tasks, but then there is some other functionality which is serial or sequential, which you cannot break down into multiple tasks. Okay, so that we are indicating as serial part and the parallel part. So let's say that we have a program that executes and finishes in one time unit. So if it's total if it is single threaded, if we run it with a single thread and it completes its execution in one time unit, then let's say S indicates the time to execute the serial part. Okay. So there are two parts, serial part of the application and parallel part of the application. Now, if let's say S indicates the time taken by the serial part and it is less than 1, then what is 1 minus L? The remaining time will be taken by the parallel part, right? But still when we are running it with a single thread. Are you getting me or not? So let's say you have, this is your application code, and like very simple example. Now this is the part of the code which you can not break down into multiple tasks, and it must be executed in a sequential fashion, which means S, okay? And the remaining part is what you can execute, okay, let me name it as serial instead of saying S. And this is, remaining part is which you can break down into multiple tasks and assign to multiple threads, okay? Now, first assume that we run this application with using a single thread. We are using a single thread to execute the whole. And this thread in total takes one time unit to complete, okay? Out of that one, let's say that S is the amount of time that is spent to execute this part. So S, So what is the time that will be taken to execute this part by that single threading application? 1 minus s, right? If this is the total time. So 1 minus s, right? This is what I'm trying to say here. So now let's say that I run the same application. First, I run it on a single core platform, having a single thread. Now I run it on a platform which has n number of processing cores, which basically mean that I can run n tasks at the same time in parallel way, right? So then parallelized portion of the program will finish n times faster. So the speed up we get is this one. The maximum speed up we get will be less than or equal to 1 over s plus 1 minus s divided by n. Serial part, time taken by the serial part, time taken by the parallel part. Now the time taken by the parallel part can be only assigned to the multiple cores, right? This part cannot be serialized parallelized anyway. Only this part can be parallelized here. Only this part can be parallelized, right? So we are assigning it to n cores. So if we assign it to n cores, then it will this time will be now divided by n. If on the single thread this part was taking 1 minus s time to complete. Now if you have two threads running on 2 cores, it will take 1 minus s divided by 2, right? Simple. So basically here what we are trying to say is that the speed up is dominated by the serial part or limited by the serial part. How? Let's say I gave you example that if we have 2 cores. Now let's say if I change it, instead of 2 cores, I have 32 cores, right? So yes, I will get the performance improvement, but how much performance I get, it depends upon the value of s. And here is a concrete example. Assume you have s is equal to 10%. Like if the total time is 1 second, so 10% of that is taken by the serial part. And you have only 2 cores, right? So if you have only 2 cores, 1 minus s, which means that 80% of the time can be run on 2 cores. So speed up will be 1.81 times. You have 10% serial part, which means you have 80% parallelizable part, right? And you are getting 1.81 times improvement only with 2 cores. Now compare it with the case where you have 80% serial part, which cannot be parallelized. Only 20% can be parallelized. And you have 32 cores. The speed up you are getting is 1.24 times, much less than this. Even here you had only 2 cores, but you are getting 1.81 times improvement. Here you have 32 cores, but you are getting only 1.24 times improvement. Why? Because there is no scope or potential for parallelization, or lower potential for parallelization, because 80% of your code is not parallelizing. Okay, so if there is no space for improvement, you cannot get the improvement, right? How you can get the improvement? If you can parallelize your code. Any questions?
So now function as n approaches a very big number,
So let's say n approaches infinity. You have infinity number of cores and infinity number of threads. So all it depends now. If it is infinity, this will become 0, right? Everything is limited by s now. If s is 10%, if s is, let's say, 0%, you will get the ideal case. If s is 100%, you will get minimum improvement, lowest improvement, which is actually depicted here. So you have this graph. On the x-axis, you have number of cores. On the y-axis, you have the speed up, but then you have 4 different lines, each for a different case. So ideal speed is the case where you have no serial part. The whole code is parallelizable. So as you increase the number of the cores, your performance will increase. The speed up will increase, right? Now, and then as you increase the serial part, the performance, the maximum performance improvement you can get starts reducing. For example, in case of 0.05, which is this green line, it is maybe like 8 times or 9 times. On the blue line, when you increase the serial part even further, the maximum performance improvement reduces maybe up to 6%, 6 times, not percent, and so on. And when you have 50% serial code and only 50% is parallelizable, your performance cannot improve beyond 2 times. Doesn't matter how many cores you have. Like you have 2 cores, you get maybe like 1.5 times at 4, little bit more, but then it starts saturating. You cannot get further performance improvement. Okay. Any questions? And actually, in the project one, when you have where you have the sample output, you see the same pattern. There we are just drawing the execution time, so it is reducing. Here we are plotting the speed up, so it is increasing. So I mean, if you just inverse it, it will become the speed up. Okay. Any questions? No? Okay. Now we have talked about different things related to the threads, but how we can actually implement the threads in the software. There are 2 options. There are 2 ways to answer these questions. We can either implement at the user level or at the kernel level. Okay. So, okay. For this setup, for the next couple of slides, you need to read, and this is required reading, section 2.2.4 up to 2.2.26 of book by the Tenenbaum. Okay. So one option is that we implement the threads at the user level code, not at the kernel level code, in the form of a runtime library. Can anybody answer the question why I'm saying as a runtime library? Why I cannot implement threads as part of each user level process? Like every user level process has its own implementation of threads. For?
Uniformity, so that way the system doesn't slow down by trying to allocate present enough.
Not really. Why we use libraries?
The user doesn't have to implement it themselves.
Yes. You have a library. All the APIs, all the function procedures needed for implementing and managing the threads are available in there. So what you need to do is you simply need to compile the library and link it into your application when you compile it, right? So now you don't need to do the work separately for each application. You don't need to redo the work, okay? So here is how you can implement, how the threads are implemented at the user level. I will go over this figure. So first thing is that when you are implementing the threads at the user level, your kernel is not aware of the threads at all. Kernel has no idea of the threads. It is not aware of the concept of the thread. It still treats each process as a single threaded process. Okay. So if you look at this figure, let's say here you have user space, you have 2 different processes. Each one of them has multiple threads, and then each one of them, the threads of each one of them are managed by the runtime system, which is basically that library. And then that runtime system maintains a table which is called the thread table. The thread table is very similar to the process table, which we have talked about in one of the previous lectures. The only difference is that thread table keeps the only thread specific information in each entry. So what is thread specific information? Like program counter, stack pointer, registers. So only that information which is required to run properly a given thread. Okay. But from the kernel perspective, there are no threads. Kernel is not aware of their existence. It still treats this process as a single threaded process, and it can maintain the process table. So one entry for each process. Okay. Yes, go ahead.
So when we're doing that approach, doesn't the library still make system calls to get those threads, or are they like virtual?
Yeah, okay. So that is actually the whole motivation behind implementing the threads at the user level to avoid invoking the system calls. So to create the threads, creation of the threads, destruction of the threads, scheduling of the threads, context switching between the threads, all is handled by the user level code. Library is a user level code. Okay. But when I will talk about it, but whenever one of the threads need to make a system level call, like let's say you need to read the data. So now read is a system level call. Now what will happen that and let's say it is a blocking system call, it will block the whole process, all the threads, because from the kernel perspective, the process is a single thread. It is not aware of multiple threads within the scope of a single process. So all those functionalities which you are talking about, like needed to create, destroy, schedule, context switch the process threads, all handled at the user level. How? I will talk about it. Okay, so you have one thread table per process, which is maintained by the runtime library or runtime system. And each entry holds only thread-specific properties and information. Kernel still maintains the process table. And user-level library, it needs calls are needed to create, terminate, schedule, or to schedule the threads. So a process, if we want to create a thread, it needs to call the user-level APIs to create or destroy the thread or schedule a thread. I will talk about how. So this is how it works. The basic idea is, so what is the idea of the thread? Thread is just a sequence of execution, right? So we need a program counter. We need the stack to track its local variables. We need registers so that we can execute instruction, and the data produced by those instructions can be stored in the registers, right? So what you do is that, let's say I have initially a thread which, of that process, user level thread, which is running, and now I want other thread to be executed. Okay. So the thread one, which was initially running, it must invoke a function, for example, thread yield, to release the CPU. If that thread one doesn't invoke thread yield, it will never be able to release the CPU, and other threads of the same process, they will not be able to execute. Which means that it should willingly it should release the CPU. And when it does call the thread yield, then what happens, to answer your question? So what happens that the code of this thread yield API, what it will do, it will store the information of the calling thread in the thread table, which basically means that here in the thread table entry corresponding to that thread, you will store PC, you will store stack pointer, you will store the register values and all other needed information. And then the code of the thread yield API, it will look at the thread table and see and to try to find another ready thread which can be run. So if it finds a ready thread, then it will read its entry from the table and load the information from that entry into the register. So it will put the value of PC read from the entry into actual PC register. All the registers loaded from the entry into like register A, B, C, and whatever. Okay, and the stack pointer. And once you do that, now what you have done, you have updated the PC, right? Once you have updated the PC, pointing to the instruction within the code of the second thread. So which instruction next will be executed within the next thread, thread 2, which basically means that now you have context switched the thread. So now the second thread will be executed. It's that simple. Did you get the idea or not?
It's a pretty ignorant question. Aren't threads like basically built into the course? Maybe in something so are they like virtual, or is there a hardware component to threads?
There is hardware component. So PC is a hardware component. So let's say you have this code. So you want to run your code. So, and let's say your CPU and your core is pipeline, right? So you have this pipeline where you have to take up the course any entry level course on architecture. So you have different stages of the pipeline. So here you have fetch, where you fetch an instruction, then you decode, which means you try to understand what this instruction wants me to do. If it is an add, you need to do addition, but you first need to find out whether it is add or not. Okay, if it is multiply, you need to do multiplication, but you first need to identify whether it is multiplication instruction or not. Okay, then execute whatever it wants to. If it wants to do addition, then do the addition. If you want to do the multiplication, do the multiplication. Fetch, decode, execute, write back, which basically means that maybe after addition, you have produced some data. So where to write that result? In memory or in some register, right? And some other stages, but these are like basic stages, okay? So, but from where to fetch the instruction? How I know from where to fetch the instruction? from which location of the memory? I find it by looking at the program counter register. So it will give me the address of the next instruction to be executed. Okay. Now, if I have, let's say, if I have 4 pipelines, basically, which means four cores, and I have 4 PCs, PC0, PC1, PC2, PC3, I can execute 4 streams of instructions at the same time, right? So this is maybe fetching from address 1, this is fetching from address 100, first instruction, this is fetching its first instruction for 200, and this is for 300. I'm just trying to make a very simple thing. Okay, so you need the hardware for.
Okay, so in this case, each one was 4. Are the threads inside within the cores?
So
or is this a way?
So these core thread itself is an idea that it's a logical thing, okay, which is stream of execution, stream of instruction executed, which is ported or which is implemented or realized by building this hardware. Okay, if you don't have PC, if you don't have 4 separate pipelines, you cannot achieve 4 separate stream of execution. You cannot achieve 4 separate thread execution. Okay. So here, what I'm saying that when you invoke the thread yield, now you store the information of the calling thread in the thread table. Let's say you have only 1 core. So the thread which invokes the thread yield, you store its PC value into the thread table, among other things. And then you look in the thread table, okay, is there a thread which is ready to run? If it is, you fetch its PC value, which was you had stored in previously. You fetch it and put it in the PC. And now the next instruction will be executed from, let's say, address 100. Okay, so which basically means that you have scheduled another thread. You have same core, but first it was used by thread 1, now it is used by thread 2. So this is how you implement it at user level. There is no kernel involved here because loading registers or storing them in the stack or somewhere in the memory is just load and store instructions. And to execute load and store instructions, you don't need to perform the system level calls. Okay, so what are the examples? What do you think are the advantages of this approach? Let me check the time. Yeah, we have like 5 minutes. Let me finish this slide. So what are the advantages of this approach where we implement the threads on the user level, not on the kernel level?
First is we don't use a kernel.
That's correct. Anything else?
It doesn't require the user to understand the lower level of the.
No, actually, that is a disadvantage because user need to know what APIs I need to call. And if, for example, if our user level thread or the program never invokes the thread yield, other threads will never be able to occupy the CPU. Because if I'm not releasing it, you cannot take it. Anything else which can be taken as considered as advantage? Portability, which basically means that since the threads are implemented at the user level library, like the API is implemented in user level library and the processes are only calling those user level APIs. So even if your kernel doesn't support the idea of the threads, you can still run the threads, right? You can build the multi-threaded application. You don't need the kernel to support the abstraction of threads. Second thing which you said, user level scheduling and context switching, because everything is happening at the user level. The operating system is not involved in scheduling and context switching, so it is less time costly. And also, yeah, okay. And you also don't need to call any system calls for thread scheduling and context switching, and also for creating threads or destroying threads. You don't need to call any system call because creation, destruction, scheduling, context switching, all of that is handled by the user level code. Okay, so which means that you need to pay the less price in terms of time. However, the problem with this approach is that let's say you have a multi-threaded application, it has 12 threads. One of them makes a blocking system call. You remember what is blocking system call from our previous lecture, right? If the call is not successful, your thread will be blocked and will not be able to make progress. It will not be able to proceed, right? Now, thread is making a blocking system call, and let's say it fails or it needs to wait. But from the kernel perspective, there are no threads. The kernel treats the whole process as a single-threaded process. So if one thread makes the blocking system call and it gets blocked, the whole process, which means all other threads also get blocked, which means there is no parallelism anymore. Yes, go ahead.
If we don't use system calls for context switching, what do we use?
If we don't use what?
System call for context switching.
Yeah, you can do the context switching as explained in this example by updating the value of the PC. So if I change it, the value of the PC from, let's say, 0 to 100. So first I was running this first set of instruction. Now I'm running the second set of instruction. And to change the value of the PC, you don't need to call the system now.
It does on the question. I can actually access the PC and registers and all that with a system call.
Yes.
Okay.
Yeah. So if you have ever programmed in assembly language, then you may be aware that you can access the registers without invoking the kernel at user level. Not all of them, but you can access the PC.
Wait, so will those libraries be like architecture dependent? Because, for example, if I have a AMD processor and Intel processor and the addresses to the registers are implemented differently.
Yes, but then what you can do is that is the advantage of the APIs, that you can keep the format of the interface same, but the internal implementation you can change. So let's say you have written a program which uses the API, and then you want to run the same program. First you developed on Intel, and now you want to run the ARM platform, but you are using the same API. Now implementation of the API will be changed, but your program will be same. Okay. So I explained why it happens that if one thread invokes the blocking system call, and it gets blocked by all other threads, because kernel is not aware of the user level threads, so it treats the whole process as a single thread. Also, if a thread never releases voluntarily the CPU, then no other threads can take the control of the CPU. Okay. Even if like there are multiple cores, you cannot run them because kernel puts a process on a core. Kernel puts the process on a core. So if I have multiple threads, I can change by updating the PC at user level. I can change the sequence of execution that I want to run. But if, let's say, in my first task, in my first thread, I never invoke thread yield, which updates the PC, then PC will never be updated, and this sequence instruction will never get the chance to run. Right? Also, remember in one of the previous lectures we talked about the interrupts, and we talked about the timers, right? So if let's say you are running one process and it never releases the CPU, then kernel maintains the timers, it allocates the time, and then it forces that process to release the CPU. But those timers are maintained at the level of process, not at the level of, they are not maintained within the process, which means that there are no thread level timers. So if there are no thread level timers and one thread never calls the thread yield, there is no mechanism to force that thread to release the CPU. Okay. So which basically means that as a programmer, let's say you forget to invoke, forget to write the thread yield API. Now this thread will never, if it gets a chance to run, it will never release. You have a while loop, and in that while loop, let's say you never put the thread yield. So now your thread will never release the CPU, and other threads in the same process will never get the chance, which means there will be no concurrency, no parallelism. Any questions? Okay, so let's stop here and then see you in the next lecture.